So thank you very much for the invitation. I think this is a wonderful event that brings together people who like technology not only for pleasure but also for business. And I would like to congratulate Vasilis and his team for this initiative. So this is the outline of my talk. I'm going to show you what is the problem that we tried to solve, what are the advances of the technology that we created, and what are the applications, and some applications. We wanted to network all the plants in a greenhouse, all the plants in an agricultural field, all the plants in your grandmother's garden. Why? Because it has been shown that you can have tremendous water savings. If you can micro-monitor the water needed for each plant, you can save 30% in terms of irrigation. And that is something that has been shown in several parts of the world. It has been shown in the University of Colorado. It has been shown in Agronomic Institute of Chania. If you monitor each plant, how much water each plant consumes or how much water each plant needs, you can save 20 to 30% of water. And this is tremendously important if you think that about 80% of the water potential from mountains, from rainfall, etc., goes to agriculture. The second reason that we want to network all the plants in an agricultural field is the fact that you can do precision agriculture. You can monitor how much fertilization is needed for each plant, so you can have healthier food and also a greener agricultural production. You will save fertilization, you will save chemistry in our stomach, essentially. What is the challenge? The challenge is that you cannot find technology which is affordable. You cannot find wireless technology which is affordable in terms of monetary cost and in terms of energy consumption. Why? Let me show you a commercial example. This is a French company that basically has built that sensor over there. It has a capacitor. Basically, you insert this capacitor inside the soil, and it transmits via Bluetooth to your cell phone, to your smartphone, how much wet is the soil. Also, it has a very nice Radiance sensor. So basically, it tells you whether the soil is watered or not, and whether there is light inside the room. The problem is that this is extremely expensive. It's on the order of tens to hundreds of dollars. So if you want to network 10,000 plants inside the greenhouse, what are you going to do? The basic problem is that existing wireless technology is extremely complex, and that's why it's extremely energy consuming and monetary-wise expensive. A typical Marconi radio transmitter has a microcontroller or processor. It has some signal conditioning animals, basically a filter, a mixer, an oscillator, and a power amplifier. That amounts to complexity, that amounts to joules, energy. That amounts to monetary cost. So basically, state of the art right now is about 20 milliamps, 60 milliwatts for ranges on the order of 100 meters to 1 kilometer. You cannot go lower than that, no matter what, because those are complex. So what we said is that let's get rid of this. Let's get rid of all these little annoying animals. And let's build a radio for each plant that has one antenna, one transistor that acts as a switch, and a logic, a very small, a very inexpensive microcontroller. So basically, create a reflection radio or scatter radio, meaning that you illuminate the antenna with a carrier, and that basically antenna reflects back that wave, and you modulate information. The plant can modulate information by very smart switching of this antenna. Basically, you modulate information on the reflection coefficient between the antenna and the MCU. This is technical. In other words, all you need is a switch. All you need is a very simple transistor. And the funny thing is that you have seen that. You have used that. Okay? This is the RFID technology, radio frequency identification technology that you have used when you go to Zara to buy your favorite clothes. There are big antennas at the exit that basically alarm when the lady at the checkout hasn't removed a very simple RFID tag. It works exactly this way. You saw it today. Dimitris, in his very nice presentation, showed you a sensor at the cow's ear. This is an RFID, and it works exactly this way. Okay. What is the problem with this technology? If we can create radios with just one switch, what is the problem? The problem is that you may have very limited range. Existing RFID range is on the order of a few meters. So we had to solve this problem. We had to create scatter radio appropriate for plant applications on the order of tens to hundreds of meters. So how did we manage to do it? We used several tricks. Basically, in typical RFID applications, the reader as also the carrier emitter, the illuminator of the initial wave. Basically, we separated those two. The carrier emitter is a different device from the reader of the scattered information. So basically, you illuminate the tag with a carrier. The tag modulates information using this trick with a switch, and you have a different machine, the reader, which in software, in smart signal processing techniques, basically can demodulate the information that the plant sends and extracts the information that you want. So the first idea is that we created an appropriate network architecture to separate the emitter from the reader. And in fact, since we can create very simple and inexpensive emitters with a few dollars, you can have multiple emitters illuminating several plants and just one reader. So we had to work on the network architecture and the algorithms for this bistatic, as we call it, scatter radio architecture. So we worked on the network. We worked a lot on the signal processing here for the scatter radio signal model, which is something really new and something that has not been explored in detail as it should. We developed forward error correction. We developed various detection techniques. We worked really hard. My students worked very hard on this, and we came up with novel designs that boosted essentially the sensitivity of the receiver and the range. We worked on the tag. Basically, you have to work on the microwave parameters of the antenna. The antenna now is not a radiator. The antenna now is a reflector. So it's completely different. You have to work on fundamental physics. You don't need radiators, you need reflectors. So you have to work very carefully on the electromagnetic wave equations. You have to go very deep on this. You have to work on the joint radio and sensor design. You have to, it's similar to the idea that Dimitris said. You have to work both on the sensing element as well as the analog radio element. Also, we worked on the efficient transmission of RF power, as we call it, zero power science. You can basically get rid of the battery here by illuminating the tag with an RF carrier and using that carrier in order to extract all the necessary energy. We work on this problem as well. And this is a picture of some antennas, some antenna grids that basically receive power from a meter 3 or 4 meters apart. So a lot of work on RF harvesting, radio frequency harvesting, a lot of work actually on energy harvesting from other sources. You can extract power from the plant itself because the plant is an electrolyte, so it's a battery. You can extract, of course, a lot of energy from the sun. You can extract a lot of power from the soil using thermoelectric principles. And of course, we developed new sensors. The outcome was that we managed to network tags, plants, 150 meters away from the reader. And I told you, the state of the art was 2 to 3 meters. Now, the state of the art is Technical University of Crete Technology, 150 meters. Okay? And as a matter of fact, our professor would be very, very proud on the work that we did on this aspect. So I'm going to show you some examples, what you can do with this technology. One very simple example is the fact that we want to monitor environmental humidity. This is the holy grail. I mean, if you talk to people who work on agriculture, they will tell you that we want to monitor agriculture in a greenhouse or in a field within 0.5% relative humidity accuracy. Well, we didn't manage to do 0.5%. As I told you, this is the holy grail. We managed to do it with on the order of 2% accuracy of relative humidity. How? So you have a capacitor here, which is a commercial capacitor of environmental humidity. It changes its value based on the environmental humidity. So we have a simple oscillation circuit here that converts changes of capacitance, changes of relative humidity, to switching frequency. Switching frequency of what? Switching frequency of this transistor. So you create basically a periodic waveform that has a frequency which is proportional to relative humidity. And you switch that transistor with this signal, essentially. And with the technology that I showed you previously, you can transmit that signal 150 meters away. We managed to do it. This is the prototype that we built, the initial prototype. Those are later prototypes. You can power it with a small photovoltaic cell. It costs in quantities of one on the order of €3, and it consumes about 200 microwatts. And also, you can have many of them. You can have many of them working simultaneously. That was the first experiment, and it was quite successful. The second experiment was a similar sensor, but instead of a capacitor that monitors environmental humidity, you have a capacitor, which is basically this thing here, that you plug inside the soil, and it measures the soil moisture. So now capacitance changes according to soil moisture. And you can basically, we want to measure how much moisture is inside the plant, inside the soil. And with the same principle, you can transmit that information hundreds of meters away. Here, that was a later design. As a matter of fact, I have it here. I'm holding it. That was the first prototype. That was the second prototype that we designed and we sent. It was fabricated in China. And this is the third prototype. This is the first version 3 that we designed it in-house, and we also built it in-house. So we don't have to send anything outside the country. We built it in the laboratory. We created a fab house in order to expedite research and development. And as a matter of fact, that was also less power consuming. We dropped power consumption from 200 microwatts to 100 microwatts. So apart from creating very inexpensive sensor for agriculture, this is another idea. Treat plants as sensors themselves. The plant itself can be treated as a sensor. So instead of monitoring external parameters, plug 2 electrodes at the plant stem and convert that voltage to using a voltage control oscillator, convert that voltage to a periodic signal that has a fundamental frequency, proportional to that voltage, and basically transmit it with the same principle. What can you do with that? Well, it turns out that plants are very, very intelligent sensors, and there is a lot of information there. Horizontal axis is time. It's about 24 hours. Vertical axis is what we measure. So the blue line here is the plant voltage, electric potential signal, as we call it. At this time instant, we water the plant. And see what happens. The voltage increases. So by monitoring the electric potential, we can find out, we can decipher not only whether there is rain in the air or in the soil, but also whether the plant itself has been watered or not. And becomes even better. The red plot is an external environmental sensor of solar radiance. So it's an external sensor. It turns out that solar radiance and electric potential signal are fully correlated. So by monitoring electric potential signal, I can find out what time of the day this signal appeared. So I can find out the clock of the plant, because plants have clocks, you know that. I believe that there is a lot of potential in this idea, and we are very hard working on this idea. So where do we want to go? We want to go to systems that have a large communication range on the order of 150 meters. We have done this. We want to have sensor and radio that costs below €1. We're about €5 right now, but it's a matter of scale. It's €5 in quantities of 10. If we scale it up in quantities of 10,000 or 100,000, it may go down. We want sensors which are completely batteryless, no battery. We are very close to that. We're not there yet, but still, it may be battery-enabled, but the battery need not be changed at all. You won't have to replace your battery at all. Or it can have a supercapacitor that stores energy with a solar panel during the day, and the sensor uses the supercapacitor during the night. And of course, we want to go to demonstrations of 1,000 nodes. Right now, the demonstrations that we have, and actually we have published them, are on the order of 50 nodes. In principle, there is no reason to go to 1,000. The designs are there, the architecture is there, the architecture and algorithms accommodate 1,000 sensors, but we want to demonstrate it also, and we will try to do it. So as a conclusion, I'm going to show you a picture of a greenhouse development of this technology. This is published, so you can basically read the details. It's a greenhouse at the Agronomic Institute of Chania, a tomato greenhouse. We collect all the environmental humidity from various points of the greenhouse, and we report them real time to a website. So basically, you can open your smartphone or your computer and basically extract all that information. This is a project funded from General Secretariat of Research and Technology. It runs for the last 3 years. This is the last year, and I would like to acknowledge their help. And also, I would like to thank my students and my colleagues. Without them, that work would be impossible. Do I have time to show the video? So let me show you a quick video. Actually, I have 2 videos. I'm going to show you one now, and during the Q&A, I will show you, if we have time, the second one. So this is the reader. This is the emitter, and inside the cooler box, we have built that humidity sensor that I talked about. Humidity, it's a dry day. It's about 23% relative humidity. So my students will move the sensor far away. You can see also the nice scenery. Chania is a wonderful place. Come and visit us. So they move about 50 meters away. The sensor is there. The reader remains at the point that I showed it before here. And let's see what the reader measures. It should measure 23% again. It's still 23%. Okay, so I'm just showing this demo to tell you that range is not an issue with RFID technology. If you are smart in terms of algorithms, RF engineering, embedded programming, PCB prototyping, etc. It's the epitome of electrical engineering. There is no knowledge of electrical engineering that has not been used in this demonstration. So, thank you very much.